Right, hello folks. This is the next little section in the ozone cell study materials. Moving on from introducing radicals in chemistry. So if you haven't watched that yet, you should watch that one first. On that subject then, if I show you something, a chemical species, CH3, just answer the question, is this or is this not a radical? And think, how would you explain that? So is this a radical? Pause the video. And so is this a radical? Explain. See what you would say. I'll start it again when you're ready. So the correct answer here is yes. And the explanation really, there's no better explanation than drawing a dot cross diagram. So don't try and put it in words. If you do a dot cross diagram for CH3, you've got 3 single bonds to hydrogens. And then you have to spot that carbon is in group 14 of the periodic table, 4 electrons in the outer shell. At the moment, we've only drawn 3. So there's a 4th electron. And then you can just say, look, unpaired electron. Use the technical vocab. That is exactly what you call it, an unpaired electron, not, a lonely electron, or, I don't know what else you could call it, but it's an unpaired electron. Okay. I guess we also practiced how they form. So if you have methane, CH4, what are the curly arrow type mechanism drawing? To show radicals forming from this molecule, and what conditions would typically cause that to happen. So pause the video, have a go, start it again when you're ready. And so this is, anytime we're talking radicals, this is the use of those sort of half-headed arrows, or just the hook on the one side. It wouldn't matter which bond you chose to break here. So we could break any one of these bonds with 1 electron going to the hydrogen and 1 electron going to the carbon. So forming radicals is always, note where the arrows start. You're breaking a bond, so they start at the bond, showing the bonding pair of electrons being lost from the bond. And then since each of the atoms in the bond is picking up 1 of the electrons, we get these kind of half-head arrows showing the movement of 1 electron in each direction. The outcome of that then would be that you would have a hydrogen radical. So traditional to draw a dot next to a radical, but you're not wrong if you don't. And a methyl radical, so the CH3. Both of those now will have an unpaired electron where a single electron went back onto them. Okay, the focus of this little video then is to look at a particular reaction of the alkanes. This is the radical substitution reaction of alkanes with halogens. So it was mentioned very briefly in one of the early videos as just a reaction you need to know involving haloalkanes. It's an unusual reaction because alkanes, just saturated hydrocarbon, don't have any functional group that brings reactivity into the molecule. So there's very little you can do with alkanes. You can burn them as a fuel. You can crack them. So we have met that. Heating them with a catalyst and you get alkenes. But apart from that, they don't have pi bonds that can do electrophilic reactions. They don't have partially charged carbons that might invite attack for other reasons. So it takes something as extreme as a radical to make it happen. Okay, so you need to know the overall reaction involved here. So if we take methane, e.g. CH4. If you react that with a halogen, let's go for bromine, it's a substitution reaction. So you're going to swap a hydrogen for a halogen. So you will get a swapped hydrogen, and then the hydrogen you've knocked off picks up the other halogen atom. So you get the hydrogen halide like that. And you'd be expected to point out that this requires UV light, and typically high frequency UV light, in order to provide the energy needed to smash that bond. So that's the overall process. So that's overall reaction. But you need to know the mechanism for this reaction. And this is going to take you probably a few times to get your head around this. So expect to have to just scan over this video a little bit. The mechanism occurs in multiple steps. So step one is a process in which radicals are made from the halogen. Molecule. So the reaction can't happen until we have radicals. Methane and bromine Br2 are just stable molecules. They're not radicals. So at that point, we don't have any radicals. So we're not going to get a reaction unless we make radicals. And so we get our halogen. So we're going to go with the reaction as shown above, bromine, and we do this bond breaking process where each atom gets one electron from the shared pair in the bond. Note the arrows start on the bond to show the electrons moving out the bond, and they have that half head to show one electron moving in each direction. The outcome of that is that we've got two bromine radicals. I'll actually write them out separately, but you could just write two BRs out of this. And in order to make that happen, you're going to need the high frequency UV light to supply the energy needed to do that. Okay, there's a little bit of vocab here that you need to know. We've already met one bit of it. This is the type of bond breaking involved here. Do you remember what it was? Just pause and have a think back to the previous videos. And the answer would be that it is homolytic. Oops. Bond fission. So if you get asked what type of bond breaking is involved here, it's homolytic bond fission, and you know it is because the outcome is two radicals, two things that are sort of equal to each other, rather than a positive ion and a negative ion that you get in the opposite thing, the heterolytic bond fission. Okay, there's further words though. The type of reaction involved here is a photodissociation reaction. And unpacking that word, photo not referring to cameras, but light, and dissociation, the opposite of association, where things kind of get together. This is splitting using light. So just look at the reaction. That's exactly what's going on, right? You're using UV light to cause two atoms that were associated with each other in a covalent molecule to dissociate, to split up from each other. And then finally, it's the type of step in a radical reaction this is some new vocab, and we'll just summarize this later, but it's an initiation step for a radical reaction. Why? Because non-radicals form radicals. Initiation is in the start of things, so you've got the Br2 molecule that doesn't have radicals, splitting into the two bromine atoms that are radicals. So you've gone from a situation without radicals to a situation with radicals. Okay, so if you want to react a halogen with an alkane, as shown in the overall reaction, bromine with methane here, the first step then is to use ultraviolet light to create radicals where there weren't any. The reason that it's the halogen, not the methane, is simply that the bonds are weaker in the halogens. So the halogen-halogen bond is relatively weak, and so it takes less energy to break it than it would to break one of the carbon-hydrogen bonds in the methane. So when you shine your UV light on, that's the bond that breaks first. Okay, so we've made the radical. What does the radical do? So step 2. The what are called propagation steps. Propagation, a word you find in gardening. You propagate plants, you sort of help them to grow. Anyway, it just keeps the reaction growing. You'll see this is what's called a chain reaction, because one step leads to the next step, leads to the next step, leads to the next step, and it will just keep going. But this is going to introduce you to how radicals react. So just look carefully. We've got our bromine radical that formed in step 1. So this is a bromine radical. And that's going to react with our methane molecule. And the way it does it is a tale of bad manners in terms of relationships. So you've got nearest it a hydrogen. That hydrogen is currently in a relationship with the carbon atom. It's sharing its electron with the carbon atom. Nice stable relationship. Actually, it appears that it's being kind of cheated on because the carbon is in a relationship with 4 hydrogens at once. So maybe it deserves to lose that hydrogen. I don't know. But what the bromine does is come along and say to the hydrogen, obviously not literally, look, I know you're kind of in a relationship with that carbon, but I drive a Ferrari, or I don't know, whatever it is that's highly appealing. Come and share your electron with me instead. I am clearly much more desirable than that carbon atom. So apologies if somebody's just treated you badly in this way and gone off with somebody else, and this feels a bit raw, but it's kind of what's going on here. The bromine atom with its unpaired electron going along to the hydrogen saying, hey, you know, I like the look of you, come share your electron with me instead of that existing share that you're doing with the carbon. And so the hydrogen's shared electron ends up in a share with that bromine instead. So just have a good look at the arrows. It's really important with mechanisms that you look at the arrows. Note that for the radical, the electron going into the bond, where is that electron coming from? It is the unpaired electron. So the radical is using its unpaired electron to start the process of a new bond forming. And for the hydrogen, where is that arrow coming from? No, it's not coming from the hydrogen atom. The hydrogen atom doesn't have an unpaired electron. It's not a radical. For the molecule that's being attacked by the radical, the arrow comes from one of the existing bonds. So the arrow starts on a bond showing an electron being pulled out of one of the existing bonds. So that bond is starting to break and going into that new bond forming. So it's really important that you look enough to kind of see the story here. The radical using its unpaired electron to sort of entice an electron out of an existing bond, with that bond starting to break to make a new bond. Of course, the CH bond has 2 electrons. And so if that bond is breaking with 1 electron going into the new HBr bond, the other one gets returned to its parent, so to speak. So with the breakdown of that relationship between the hydrogen and the hydrogen goes off in a new relationship with the bromine, and the carbon gets its electron back. So the outcome of that is that we've got the Br now attached to the H, and the carbon without the H having picked up a radical, an unpaired electron to make it a radical. So this is now a new radical. It would be called a methyl radical because it's like a methyl group when we have branching on carbon molecules. Okay, now that's clearly not the end of the story. If you look at the overall reaction, what we had was methane reacting with bromine to make bromomethane and HBr. At the moment, we have made HBr, sure. We haven't made bromomethane though. We've just made a methyl radical. Radicals are highly reactive and unstable, so that can't be the end of the story. And radical reactions are chaotic. So there's all kinds of things that could happen next, but they would mostly be pretty irrelevant. So for instance, that methyl radical could go and steal a hydrogen from another methane molecule. But if it did that, the CH3, the methyl radical, would grab a hydrogen and become CH4, and the other methane that it was reacting with would become a methyl radical. So nothing has changed. It could potentially pick up one of the other bromine radicals that formed in the step 1, the initiation step. But that would be using up radicals, and the reaction would stop. So the only thing that keeps the reaction going, and hence the only thing that's worth talking about, and the thing that's most likely to occur, is that the methyl radical, having formed in that first part of step 2, bumps into a bromine molecule. Okay, so this introduces a problem for some people. They go, well, hang on, step 1 showed the bromine molecule breaking up into bromine radicals. So I'm just going to add a note here that this happens, this happens to a few bromine molecules. But the reality is, if you're doing this reaction and you're mixing a bunch of bromine with a bunch of methane, you're going to have billions and billions of bromine molecules and billions of methane molecules. So when you make the reaction mixture, you've got lots of bromine molecules, a few of them split up. So when you form your methyl radical and the first part of step 2, one of the most likely things it's going to bump into is one of the billions and billions of bromine molecules that you put in as a reactant. Now, the way this step's going to happen is exactly the same that we did above, how radicals react. So see if you can just sort of predict and picture what that looks like. We have now not the bromine, but the carbon with its unpaired electron going to one of the bromines in the Br2. Hey, look at me with my incredibly cool haircut. You don't want to be in a relationship with that other bromine. It is a loser. Come and share with me instead. So we have a transfer of relationship with the electrons from the shared pair between the two bromines going round to that new share with the carbon atom. Of course, there's 2 electrons in the bond, so what happens is the other one goes on to the bromine at the other end. So once again, have a look at the arrows, see where they start and finish. We've got an arrow from the unpaired electron on the radical going into the new bond between the carbon and the bromine atom. And to the same location, we have one of the electrons coming out of the existing bond in the Br2. The other electron from that bond goes on to the bromine at the other end. The result of this is that we now have the CH3 with the Br attached, and we have a bromine radical. Okay, so now, have we achieved what we said we were going to achieve in the overall reaction? In the first part of step 2, we made HBr and a methyl radical, and that methyl radical then carried on to the next step, reacted to make a bromomethane, CH3Br. So we have done what we said was going to happen in the overall reaction. We've had methane molecules, we've had bromine molecules being fed in, and coming out, we've got bromomethane and HBr molecules. So this is the reaction. There's just a few things to say here. A little bit of vocab. the CH3 radical, the methyl radical, is made here and then used up here. Should have done a different color there, shouldn't I? Just to avoid confusing my lines. So we've come across this word before, something that is made in step 1 of a reaction that is used up in step 2 of the reaction, or made in one step and used up in a subsequent step. So it's not actually a reactant that you're putting in at the start, and it's not a product that's coming out at the end. Do you remember a word for things like that, that are made in one step and used up in another step? The word is intermediate. So an intermediate is something that's formed during a reaction. It's not one of the reactants you put in, and then it's used up before the end of the reaction. So it's a kind of a temporary substance that forms during the reaction. Okay, we also have, though, if you look, we've got this bromine radical at the beginning and there at the end. So what name do you give to something that is present in a reaction, takes part in a reaction, seems to be necessary for a reaction to happen in any noticeable way, and yet remains chemically unchanged by the reaction? What name would we give to that? Hopefully something springs to mind. So we would call that a catalyst. Okay, so the point is with this, that the Br radical used in the first bit, in the first part, is reformed in the second part. And so the two parts of step 2 keep happening until all the CH4 and Br2 is used up, or the radicals are terminated. More on that in a moment. Okay, I realize there's quite a lot of information here. Like I say, you might well have to just scan through this video a couple of times to make sense of it. It's just something you're going to have to get your head around. So feel free to pause and take a breather at any moment, but do persist until it makes sense. Okay, so that's step 2. Step 1, remember, was the radicals forming, UV light shining on the reaction mixture and a few of the bromine molecules breaking up to make some radicals. Those radicals then go to action in step 2, attacking methane to make a methyl radical, which then attacks a Br2 to make another bromine radical, and on it goes. So just a little bit of vocab here. This is called a 2-step catalytic cycle. And hopefully you can see why that is. It's there's 2 parts to step 2, involving a catalyst that go round in a circle effectively, with the bromine radical being used up in the first step and reproduced in the second step to do its thing again and again. It's also called propagation. So these are propagation steps. Why? Initiation, if you remember, was non-radicals forming from radicals. Propagation steps are where radicals react. Radical reacts, producing a new radical. So whereas initiation went from something that wasn't radical to something that was radical, propagation steps like these ones, if I just go back to them, use something that is a radical. So in the first part, the bromine radical, to produce something else that's a radical. So the product is the methyl radical. And then in the second part, the methyl radical is used to produce a different radical, the Br radical. So they are using up and producing radicals, so they kind of maintain radicals. The other thing to show about this is that you can look at the overall effect of step 2. And you just write out the 2 steps. So the first step was Br dot plus CH4 goes to the HBr, where it's grabbed a hydrogen plus CH3 radical. And then in the second part, the CH3 radical reacted with another bromine molecule, Br2, and you got the CH3Br and the Br dot. If you want to know the overall effect of steps that happen one after the other, you can effectively add up everything on the 2 sides. So if we add everything on the reactant side of the 2 steps, we end up with Br dot plus CH4 dot plus CH3 dot. Br dot plus CH4 plus CH3 dot plus Br2. Going to everything on the right-hand sides, HBr plus CH3 dot plus CH3Br plus Br dot. Notice it doesn't matter which side the dot goes on. Now, you never write an equation where you've got identical things on both sides. So have a look on the both sides. What is it that can be cancelled out? So hopefully you spotted the Br dot. That's the same on both sides, so we can cancel that. There's no point having something that's equal on 2 sides of an equation. And the other thing is the CH3 dot. So we'll cancel the identical things. And then we can write what's left. So we end up with saying CH4 plus Br2 goes to HBr plus CH3Br, which lo and behold is what we said the overall reaction was going to be. Okay. Finally, so that was step 2. We need step 3. Which is what's called termination of radicals. So step 2 just had that bromine radical being constantly regenerated. And so the reaction could just keep going, cycling through those 2 parts to step 2, over and over and over, using up methane molecules, using up Br2 molecules, and producing products. So the radicals are, once they've made, they act as catalysts, they don't get used up. So they allow the reaction just to go on and on and on and on and on in a chain reaction, one step leading to the next step, leading to the next step. How does that reaction ever finish? Well, you might run out of reactants. That still leaves radicals that are going to go off and terrorize the world. So once you've made a radical, have you sort of opened a Pandora's box? never mind if you've never heard that reference before, unleashed some kind of force of evil in the world that is just going to go around smashing things up, grabbing atoms off other things, destroying relationships. No, they eventually meet their doom when they meet another radical. So this is unpredictable, exactly what happens. You just get one radical. So let's say one of the bromine radicals happens to bump into another bromine radical. Actually, I'll put the dot on the other side. And maybe you can see what's going to happen here. They both have an unpaired electron. Rather than going off and smashing up somebody else's relationship, they meet each other. Their eyes lock across the room. They go, "Oh my gosh, look at you, an unpaired electron as well. You understand me. We're going through the same thing. Let's get together and meet all of our deepest longings to pair up our electrons. We're just made for each other." And so there we go. It's a happy outcome for the two radicals. So we could have that, but equally we could have the two methyl radicals meeting. And that would be a termination step as well. So if one of those met one of those, again, romantic moment when they realize they both have an unpaired electron and they say, we could pair. How about that? Exciting times. And so we end up with ethane. You could equally, if you're sitting there going, well, but why can't a bromine radical bump into a methyl radical? Well, they can. This is all just anything that can happen. Any two radicals can meet and react to pair up their electrons with each other. In this case, you will get a bromomethane molecule. That isn't the main source of bromomethane forming, because it wouldn't keep the reaction going. The reaction would be over very quickly if the bromine radicals got used up in this way, and then it would just stop. So lots of possibilities for termination. So we just need to understand what's meant by a termination reaction. So termination equals a reaction in which radicals react to make non-radicals. Like that. Okay, so we've got this quite sophisticated process. If you want to make a halogen react with an alkane, overall you're going to get this substitution. But the way it happens is, first of all, smashing up some of the halogen molecules with UV light to make radicals so the reaction can actually happen. Those radicals then diving in to this two-step catalytic cycle with propagation steps that just goes round and round and round and round, using up methane and bromine to make the HBr and bromomethane products. But along the way, it's possible that radicals meet each other and terminate, and then that kind of prevents the reaction carrying on with that radical. Right, just a quick summary of radical reactions. The steps involved. We can do a sort of little table here. So if you say what's the type of step, and then in the reactants and in the products, what's present. So in the initiation step, in the reactants, no radicals, but in the products, radicals. For propagation, in the reactants, you've got at least one radical. And in the product, you've got at least one radical. So it keeps the radicals alive. And then termination. In the reactants, you've got radicals. But in the products, you've got no radicals. So effectively, in initiation, radicals are born where there wasn't any. In propagation, they're kept alive. And in termination, they're killed off. And those steps can happen pretty randomly. So just note what we've shown here is kind of the main process that does the overall reaction, reacts the alkane with the halogen to make the hydrogen halide and the haloalkane. But radicals just attack anything. So once you've made a radical, it will go pulling off atoms off anywhere. So note, you know, as you start to make increasing amounts of bromomethane, the radicals could come along, a bromine radical could come along and pull off a second hydrogen from a bromomethane molecule, potentially putting more than one bromine on, and all sorts of mayhem can happen. So I'm just going to add a little note at the end. Radical reactions. Radicals are highly reactive. So they give fairly uncontrollable reactions. Producing an unpredictable mixture of products. Sure, they might give you what you want, but they'll probably give you a whole bunch of other junk as well. So to that end, they're avoided if possible. If you can find a better way of making your reaction happen than using radicals, then do that. Oof. Okay. I'm sorry that was a fairly big chunk, but there's not much point splitting it up. It is definitely probably one of the most complicated mechanisms to get your head around. Not that that means I'm saying you can't get your head around it. I'm just saying don't expect to get your head instantly around it. What I'd suggest you do, though, is just have a go. It's not just bromine and methane. Let's say if we react Cl2 with ethane and UV light present. Can you suggest an overall equation for the reaction? And then what about the mechanism? Okay, so I strongly suggest you have a go at this. If you're thinking I don't have a clue, then just watch the video again, maybe on like double speed or something, until it starts to make sense. Pause and have a go at this, and then start the video again when you've got something to check. Okay, the answer is that you should have said, you should predict just the simple substitution. So Cl2 plus ethane, I don't know how you're choosing to represent it. I'll just draw it a bit full structurally. And you just predict one hydrogen will swap. So you'll get chloroethane, doesn't matter where you put that chlorine, they're all the same, the positions. So always just predict that one hydrogen replaced with a halogen, and the hydrogen that's knocked off hooks up with the other halogen atom to make the hydrogen halide. And then the mechanism, you show the, you might as well label the steps. So let's start with initiation. And you show the halogen, draw out the molecule full structurally. You show the bond breaking with one electron going on to each atom, giving you the two chlorine radicals. You could write them out separately. Then we've got the propagation steps. And in the propagation steps, we have the chlorine radical coming along and stealing a hydrogen from an ethane. Again, doesn't matter where you show it attacking, but what does matter is your arrows. One arrow from the unpaired electron into the space where the new bond is forming, the other arrow from the existing bond, the CH bond, into that space, and then also an arrow from that bond onto the carbon. Remember, just sort of half ahead, so hook on one side to show one electron moving. That then takes you to the situation where you've got an HCl, and then you've made a methyl radical. So where the hydrogen came off, you've got an unpaired electron like that. And then you've got a second propagation step, because that just leaves an unstable ethyl radical, where that ethyl radical attacks, and this is the bit that people seem to particularly just struggle with. Remember, not all of the Cl2s got smashed up into radicals, just a few did. So actually what you've got in your reaction mixture at this point is a whole bunch of chlorine that was put in as a reactant. So the most likely thing that ethyl radical is going to bump into that has any useful effect for the reaction is a Cl2. And it's exactly the same pattern. It uses its unpaired electron to form a new bond to the chlorine, so arrow from the unpaired electron into the space between the carbon and the chlorine, and then the existing bond between the two chlorines breaks, so an arrow from that bond also into that space to show two electrons in total moving to make a new shared pair between the carbon and the chlorine. The other electron from that CCl bond, ClCl bond, goes on to its owner, the chlorine at the other end. And so the outcome of that is that we've got now the substituted ethane. So we've got a chlorine there, we've made chloroethane, and then we've regenerated our chlorine radical. So just note, this is this two-step catalytic cycle again. We can then transport that back to the beginning to do its thing again. So these two steps just go round and round and round, using up the chlorine radical, regenerating the chlorine radical, which can attack another ethane, and so on and so on and so on. And then termination, any termination step would be fine. So what they'll say in the mark scheme, if you get asked a question like this, just anything that is reasonably sensible. So I'd say the simplest thing you can do is just say, hey, what about if two of the chlorine radicals meet and they just join back up to go back to Cl2, like that. Okay, I hope that with a few looks that starts to make some sense. I will leave it there for now.